Hello, everybody. Good morning. And I'm trying to speak about a little about our work in our group. I give the name New Materials based on 2D building blocks. But firstly, it's a good time, and gratitude is everything in our life. I'd like to thank you, my sponsors, especially the CEPID, for supporting me in my research and being in several conferences. But we can go to graphene. There are a lot of excitements about graphene. Graphene has impressive electronic, mechanical, and thermal properties, which can be applied in several applications, like sensors or make materials. There is a lot of attention to graphene, even in Brazil, when you have a specific center for this proposal. In the surfing in this wave, we have many other 2D structures. And like graphene, we have hexagonal boron nitride, molybdenum disulfide, and many others. And each one has specific properties. So graphene is a good thermal conductor, but BN is not. But you can mix these structures, the 2D structures, to build new specific materials for many proposals. And how can you do it? You can do it make mixtures. You can make mixtures in plane, like a puzzle. You can take graphene and BN, or graphene and this molybdenum disulfide, and make this kind of puzzle and tuning the specific properties. Or even you can make Legos. So you can make your planes, you can mix the planes, and you can assemble the plans to make this kind of van der Waals interaction. So nowadays we have spent like 4 or 5 years in our group to develop the pieces to build, to assemble. So now it's time to assemble these structures. So, and it's time to do it. Now you have the pieces, you have enough computational resource, and you have a good force field. I'm going to show you many simulations using a reactive force field. So you can make reactions and build and synthesize many structures using this kind of force field. In our group, in specific my part, our group head by Professor Douglas Galvão, who will give you a talk, and this morning we have mainly 4 parts. We obtain, we modify, we assemble, and we make applications with 2D and now 3D materials. I don't have time to talk about every item here. So I choose you obtaining and assembly. But we have a really nice papers about modifying and making some applications like nanocones. I will start with assembly. So you can use graphene and many other 2D structures to build foams or to build materials with really nice mechanical properties. This is a foam, and you use a graphene oxide. Graphene oxide is kind of brittle when you have just a graphene oxide and you make the foam. But you can put some reinforcements here based on boron nitride, really small quantity of boron nitride, and you have a completely different mechanical properties. This cannot be broken easily. So this is a simulations about one piece of this foam. When you have graphene and you put just one piece of boron nitride, you change completely the mechanical property. If you see here, when you stretch this structure, you see completely different fracture pattern in the structure. When you have graphene oxide, this modification is dramatically increased. Like when you have here you have BN and here you have graphene oxide, and you see when you put just a small piece of boron nitride, the failure or the structure behaves completely different, and this is in the process. It's like when you have a balloon, and you have a balloon and a needle, and if you can blow up your balloon, but when you put a Scotch tape in the balloon, you save the Bory balloon. So the boron nitride reinforce the structure and can make this kind of foam much better. Our group have that was our first foam, but our group has been specialized in many other foams. This is another work. We have the same graphene oxide, but now you have zirconia to fix the structure or to reinforce the structure. So this is one example how can you assemble the 2D materials to build foams. Nowadays, this is a 2016, we have not published. We are using graphene oxide and hexagonal boron nitride to improve or tuning thermal conductivity in epox structures. So you see here just a small quantity of graphene oxide and hexagonal boron nitride can improve dramatically the thermal conductivity in these structures. So we have a way to assemble 2D structures, but we need the pieces. We need the pieces of our puzzle, or we need the Lego. And we have to improve how we obtain the graphene or graphene nanoribbons or BN nanoribbons, or the pieces of the foam or the assembled structure. This is an example how can we develop it. This is a part experimental, part theoretical work, and it's quite simple. We have carbon nanotubes, and you accelerate the carbon nanotubes and hitting against a metal target, and you see which are the resulting structures. We can do it using this quite modern machine based nowadays on NASA, close to Rice University, and you can use a vacuum to make the process to accelerate into here and hitting against the target. And what we saw from the experimental point of view, we see this kind of structure. When I saw it for the first time, I guess it is graphene nanoribbon, and this was confirmed by simulation and more experimental data here. So here's an example about the simulation. You have the carbon nanotube, and you hit against this metal. You see the stress pattern will concentrate in the center because the structure bent inside and broke these bonds and open. So you can do really nice carbon nanoribbons or nanoribbons made by carbon in a specific way, just using a really easy process. Here is this for single layer graphene nanotube, but you can do the same for multi-layer, and the process is completely different. When you don't have the bending into carbon nanotube, but you have the flatness in this part, and you see two graphene or a bi-layer graphene nanoribbon. We are improving. This is a quite general method. We have improved this process and studying for boron nitride nanotubes. And you see, even the process is quite different because you have a different resulting structure. You can do the same with boron nitride and obtain a quite nice boron nitride nanoribbons. And you can see this will be published, I guess, in this week. You see for boron nitride. So using this really easy method, you don't need chemical approach. You just use a machine and you can obtain the pieces for assembling and using your application. But I said you a lot of good words. It's a general process. It's a one-step process. You don't need to clean the carbon nanotubes, the carbon nanoribbons, and it's chemical-free. Give you a high-quality graphene nanoribbons. You can use even for electronics. You don't need to use just for foams or just for mechanical properties. But there's a quite a big problem here. You have a high initial cost because you need that machine. That machine, there's just two machines in the world. One is in NASA and another is in the neighbor and the Rice University. So we need a really easy way to get carbon nanoribbons because we are mainly in Brazil, and we have to develop a low-cost way to get carbon nanoribbons. How can we do it? Even me, a theoretician, can do it using this approach we have developed last year. And I show you it's quite easy, and I guess here in the lab, in the chemical lab or any lab, even in your kitchen, you can do it. Here's the multi-wall nanotubes, and we functionalize the carbon nanotubes using two groups, like OH and COH. So this kind of pounder you can buy for a kind of $500 1 kilo. It's quite cheap. So you use 2 pounders and you combine the 2 pounders and you open or unzip the carbon nanotubes and get carbon nanoribbons. This is quite really easy method, but nobody has tried before. So this is how can we do in your lab, in your kitchen. Use a pounder and put 2 different pounder and use mortar and pestles in your lab, your farm, in your pharmacy, your lab, and it's kind of cooking. And you macerate. It's kind of what you do with your onion or garlic. And you see here water, a lot of water. And how can you open the carbon nanotubes using this really simple approach? And I will answer it for you, but I don't know why the people don't try it before. So it's a kind of base chemistry. Use OH and COA, they combine. Here's an example. The mass spectrometry will corroborate with what I'm telling you. Here you have like the water formation, and some pics here show you the CO2, sorry. And the method we have proposed is when you have the COOH and OA, they will combine to result in the water and the CO2. This is quite easy. So it's chemistry, basic chemistry, and this is reaction will provide you energy. This energy, the local energy, is quite enough to break these CC bonds. We have simulated to make like a quite complex process for molecular simulations point of view. We divide this the simulation in 2 steps. The first one, we calculate the reaction, how much energy this reaction will provide for graphene, for carbon nanotubes, functionalized carbon nanotubes, and if this energy is enough to break the carbon-carbon bonds and to to open the graphene, to open the carbon nanotubes. I have used lamps for it, and here I'm going to show you ReactSF, but we have like compared with density functional theory as well. Here's the first step. The first step, we have the initial state and the final stage, and you use the NAB. Some method will create many replicas here, and we calculate many replicas and optimize the replicas to try to see the reaction path in the direction. And you see for many distance between these two tubes how much energy we need to start the reactions. We see here just the mass rate can start the reaction, and how much energy it will be need or it will be provide. You see this reaction needs to be energy assisted. So we need to provide energy to transpose the barrier. But after you transpose this barrier, you saw this exothermal reaction, and this will provide you 25 kilocal per mole. This energy is enough to break the carbon-carbon bonds. To simulate it, we use a method when you have the carbon nanotubes, and we provide just in one part, in one specific part, more energy or extra energy to simulate these local energy provided by reactions. We call it by heating spot in this area, and we simulate for several energy values. And you see just 14% of provided energy by the reaction, just 14% of the energy from the reaction, it's enough to break the carbon-carbon bonds. So the method is we could simulate the method and compare it with experimental results. And what is really nice, this was our first paper published last year, but this is a really general method. And we have improved the method a lot, because this can provide you like 5 or 10% of carbon nanoribbons. But nowadays you can improve this scalability of this method and use many others like functionalized carbon nanotubes, which will provide you carbon nanoribbons. So this paper we have published like this year, I guess 3 weeks ago. And in the carbon, you see many other ways to open carbon nanotubes using just basic chemistry. So I provide you 2 ways to get carbon nanoribbons, or 2 ways to get the piece to make to assemble or to make foams, or to use for many other proposal. I will show you now my last slides, or my last work here for you. This work we have developed here at Unicamp. So there's no any international collaboration used like with Professor Stanislav, and we have developed a way to, when you have just graphite, it's quite simple, and you can burn graphite layer by layer and get like a graphene. So it's a easy method to do, and we have developed here at Unicamp. So it's quite simple. You use like an electron beam here in this part, and you can use, when you have like the suspended graphite, or you have graphite on substrate. When you have the suspended one, you see burning layer by layer graphene. So you see one layer burn, another layer burn, and when we have substrate, you see like just a whole in the sample. I show you like here. So to make the simulations, there's a trick here. Why the people cannot do it easily before the Stanislav experiment? Because there's code walls here. So the trick in the experiment and the trick in the simulations is provide code walls, protect the edges of graphene. When you protect the edge, because the edge is the more reactive part of graphene, and this, the graphite in this case, you can like burn the layer, the complete layer graphene before the subsequent one. So to make the simulations, we use like graphite, and we simulate the graphite, in this case 2 layers, and put oxygen. And we use a ReactSF, and this is some parameters. And but the trick here is protecting edge. This is in the experiment. This is in the simulation as well. And this show you. Try. This is like the simulation, then start to burn graphene layer by layer. You see, like the first, when you create enough defects in graphene, these effects will increase or consume the first layer completely before you start to consume the second one. So when the first layer go on, they start to make many defects in the second layer and burn the second layer as well. As you see here, this is a kind of some snapshot of the simulation, but I like this top view because see, like when you start your simulations here, I'm not showing you the oxygen atoms, and when you start when you protect the edge, the oxidation or burning start making a lot of defects around the structure. So these effects will increase so fast and burn the first one, because this area is much more active than the second one, the second layer. So the system prefers to burn the first layer, the energetic balance prefer to the first layer, and after the second layer. And here you can, it's over. And here you see like some the carbon-carbon bonds. You see clearly the first layer is over, and when the second layer will start. This is like a Brazilian collaboration here at Unicamp in CCES, and here how the burning occurs. In the first moment, you have a complete combustion, and in the second moment, you have a incomplete one. So, like 25 minutes, and this is the main conclusion of this work. And now, just to summarize what I have told you, like we are working with assembly and obtaining the pieces to assembly. So I have shown you like how can you assemble using a boron nitride and graphene oxide, and how can you obtain the pieces of your puzzle or your Lego. Thank you very much for your attention and invitation.
Questions?
35, tá bom.
Are they doing the chemistry correctly? They are physicists.
Yeah, I'm a physicist.
I have a question. Is regarding the first part which you showed with 2 layers, you used a very small one to protect the other one, the bigger one, from a fracture. So I was wondering why a very small piece of, of this second layer is able to protect a very big one, and why the fracture starts there, and why the fracture starts in a different point. So,
Like,
because I was supposing when you compare is that my initial guess, that the fracture should start at the point where you are putting the other layer. But in both cases, the fracture starts at a different point.
Like I show you. Like, here.
Yeah. So if you look at the bottom, the fracture starts at the edge.
Yes, exactly.
And not at the center. So I was wondering why this very small piece of the second layer protects the whole.
Yeah, like you have a reinforcement in the center. Like a good way to think when you have a balloon, a party balloon, and you use a needle to blow up the balloon. So when you put like a Scotch tape, you protect that area. Like in this area, you anchor this area, so the stress don't concentrate in that area. So the stress will be concentrated in the edges. So because of this, the will break in the edge. It's kind of a magic when you have you tried with balloon? Huh? I didn't find a movie to show you.
So the patch of this boron nitride, is that boron nitride, right?
Yeah.
So the boron nitride patch protects the surrounding.
Exactly. It fix anchor that
Anchor the
part.
surrounding. So that the stress instead of spreading out throughout the whole sheet, it goes to some points far from the patch.
Perfectly.
And so the energy concentrates in other regions away from the patch.
Yeah.
So
This
how that
is a quite.
there's something wrong with the
This is a quite general, because you can do the same with the zirconia as well. Like you need just something to anchor that point.
Yeah.
So because you have the van der Waals interaction between the graphene and the boron nitride or zirconia here, and when you have it, like you anchor that area, so
yes.
you avoid the stress concentrated that part.
And this is just not just confined to the very neighborhood of the very vicinity of the patch, but it's also a few atomic radii
It's
around.
It's the same concept on concrete. When you add some pebbles,
Yes.
then you increase the mechanical strength of the.
Have you tried different formats?
Yeah, this is like I show you a general concept, but because here I have shown you just a small piece but you can try with many different shapes, no? But this is not quite important because the stress will be concentrated far from that area, not like sensitive to local effects, really local effects like in the edge.
Can you envisage a patch that would do harm instead of good to the? So it make it weaker. Can you? Is it possible, or it's just? The question is, is there chemistry in there, or is just because the patch absorbs the energy?
Yeah, it absorbs the stress. No,
It
like
absorbs the stress.
yeah, like
That's a good question.
it's a good question, but like because here it's a kind. I try just to show you. It's a van der Waals interaction. So the van der Waals interaction will fix that point. So I don't believe any like weaker, like make weaker that part. You are going to reinforce that part. Maybe you can assemble many patches and make another area weaker than the like
Let's say,
like
let's say
if you use 2 or 3.
The question is, in principle, it only works if you have a stiffer reinforcement, right?
Yeah, exactly.
So the question, if you do the opposite, if you add a small graphene piece into boron nitride,
Yeah, I have tried it.
It
Yeah,
work?
yeah,
it works.
works, but like seamless, like because
But
The difference is so big, so you don't reinforce enough to see any like mechanical.
Do you de-enforce bottom right track?
No, you don't reinforce. You reinforce, but not that much you see. Like, because it's like when you have a concrete and put like a piece of paper. Like
Yes,
you
you know.
reinforce a little, but you cannot see
Em vez de
it.
brita, estou pensando em colocar isopor no concreto.
Ah, okay. Yeah, when you put inside, yes.
Explain this in Portuguese. Isopor? Isopor.
Styrofoam.
Styrofoam. Como é que é isso?
Isopor.
Telpopor?
Isopor.
Isopor. New word in Spanish. Isopor.
Em português.
Yeah, but here you have 2D structure, so you have one on top and not. But you are correct.
I understand that. So it's not. You never.
No, when you have just
You haven't seen
the assembly, no. But when you put inside, like when you have concrete or anything, and put inside, like when you put an epox. Well, when you put in epox, for example, in epox in the structure, like in the combined structure. So in this case, you can make weaker or harder.
I guess you could breaks in the structure if you put material that on top of graphene that induce like a chemical reaction that actually reduce the formation of cracks inside graphene.
Yeah.
Like you showed in the last example that you put the CO.
Yeah, when you use some metal nanoparticles, for example, if you deposit nanoparticles, you can like make some breakings in graphene and make that area weaker. Yeah, but via on the top. Yeah, you can cut graphene using some nickel nanoparticles, for example. Yeah. So, but these involve chemistry, and here the idea is a van der Waals interaction, just van der Waals interaction.
Okay, so when you say just van der Waals interaction, so those simulations are not with the reactive potential?
Yeah, it's reactive force fields because you need here in the reacts force field you have a van der Waals interaction
Okay,
as
so
well.
But there's also a binding well, right? There's a.
Yeah, here because you cannot see the breaking without a react
What I
F.
was going to ask you is that if you can see as you increase the stress there, you can see the vibrations on the bones increasing, and then maybe locate where the bone is going to break, and what happens to the, especially what happens to those vibrations right underneath the patch. If like the presence of the patch dampens the vibrations or not. Can you see this kind of effect there?
Yeah, we can see theoretical, but nowadays I don't have any news about experimental.
Of course, you wouldn't be able to see experimentally, but it would be a nice way to see how the effect of having the patch there
Yeah,
is making it stronger.
The change.
If you see some transfer of energy to the patch, or I don't know if it
Yeah, it's a kind of anchor, no? You like the atom, like in the bottom, will be anchored and then on using the top.
I have a picture, I'm not sure if it's correct or not. In the absence of the patch, all the stress must go to the bonds. When you have the patch, the stress can be radiated from the bonds and propagated into the, absorbed into this patch material. That's some sort of a buffer of a energy absorber when you stress. It seems to be something like that, so that
but the patch is rigid. It's a more rigid material than the rest.
Rigid,
It doesn't
yeah.
absorb much of the energy. It's not in vibration.
they've done the other way around. They have done
Or
material and added a softer material, and that also helps
Yeah, you can actually see
The
where the
context
image
is
is
different.
going, actually. Actually,
In microscopic scale, when we use the patch like that, the stress concentration depends of the relative stiffness of both materials. And normally, you try to put a patch with a stiffness not too much stiff than the material, because if you put that, the stress concentration arrives
in the edge of in the interface, yeah.
in the here.
Yeah,
different
sure.
apparently, no?
Yeah, it's different because here the interactions, I guess, is it's bigger. The interaction, the van der Waals interaction is bigger than when you have the micro scale. In the micro scale, no. But you see, like even for zirconia, because zirconia is not that small, not that like BN, and you have like the same effect. The interaction, the van der Waals interaction is locally, so you can like anchor the structure much better than in micro scale.
Nice discussions. Any further questions? If not, let's thank Pedro again.